Ok, buenos días a todos. Les doy la bienvenida a este último seminario del año del Laboratorio de Resonancias Magnéticas. En esta oportunidad, y con mucho agrado, presento a Jordi Sort. Nos va a dar una charla invitada desde Barcelona. Em, Ahora les cuento un poco sobre la trayectoria de Jordi. Jordi obtuvo su PhD en Ciencias Materiales de la Universidad Autónoma de Barcelona en 2002, con un reconocimiento de Extraordinary Award. Realizó su postdoc en SpinTech y en el laboratorio Argo en Estados Unidos. Actualmente es el líder del Group of Smart Nano-Engineered Materials, Nanomechanics and Nanomagnetism, GNM3, en la Universidad Autónoma de Barcelona. Sus actividades de investigación están enfocadas en la síntesis de una amplia variedad de materiales funcionales, películas electrodepositadas, estructuras litografiadas, materiales porosos, etc. Y su estudio, y el estudio de sus propiedades térmicas, magnéticas y estructurales. Su actividad de investigación ha sido reconocida por varias instituciones, entre ellas por la Sociedad de Física Catalana, también por la Sociedad de Física Real Española, de la cual obtuvo un premio a investigador joven en física experimental en 2003, por la Sociedad de Materiales, por la Federación de las Sociedades de Materiales en 2015. Actualmente ha supervisado 16 tesis de doctorado y actualmente co-supervisando 5 más. Ha publicado alrededor de 330 artículos con cerca de 11.000 citaciones, un índice de impacto de 51, y ha obtenido 6 patentes y ha administrado 33 proyectos de investigación entre nacionales e internacionales. Jordi, es un honor tenerte como invitado en este último seminario del año del Laboratorio de Resonancias Magnéticas. Dejo de compartir mi pantalla y la audiencia es tuya.
Muchas gracias, Luis, por la invitación y por la presentación. Ahora vamos a probar otra vez esto, a ver si funciona. A ver qué veis.
Ahora veo pantalla completa.
Sí,
Sí.
Y si paso, la siguiente va bien, ¿no?
Sí, ahí veo la segunda, así que parece
Okay.
que anda todo bien.
Bueno, mi charla quizás la doy mejor en inglés, ¿no? Porque me imagino que hay algunos nombres por ahí de gente que probablemente prefieren el inglés. ¿Va
Como
bien en
prefieras,
inglés?
como
Tengo
prefieras.
todo.
Eso
¿Da
de
igual?
siempre
Vale.
es a elección del orador.
A voluntad. Bueno, como las slides están en inglés, pues igual en inglés me va mejor. Entonces, bueno, welcome everybody and thank you for the invitation. It's a pleasure to be here, and my talk is on magneto-ionics, international metal oxides and nitrides, and the potential applications of this effect for neuromorphic computing. So the outline of my presentation will start with an introduction where I will explain the problem of heat dissipation during magnetic actuation. What are the different mechanisms to control magnetism with voltage? This is called converse magnetoelectric effect. In particular, I will explain what is magneto-ionics and how it can be useful for neuromorphic computing in the future. Obviously not yet, but in the future. Then I will focus on the results and discussion, and mainly I will show results from 2 different systems, cobalt oxide and cobalt nitride. Maybe I can try to use the pointer. Yes, okay. In both systems, very interesting is that the materials, cobalt oxide and cobalt nitride, are paramagnetic, but if we apply voltage, they can become ferromagnetic. So this is what we call on-off magnetic transition. Then I will show the advantages of nitrogen magnetoionics compared to oxygen magnetoionics and how this can be used to mimic synapses. And finally, I will point out some conclusions. So you all know that to write magnetic information, people use electromagnets, small electromagnets, where depending on the direction of the applied current, there is a magnetic field here in the gap, which can be oriented to the right or to the left. And in this way, you can orient the bits of the magnetic medium. But whenever there is a current in a wire, there is the so-called Joule heating effect. So this means that there is heat dissipation and it is actually proportional to the square of the intensity. As a consequence, about 40% of electric power that reaches a computer or data server is wasted in the form of heat dissipation. And this is actually a problem of economic transcendence. And also it can be bad for the media because the information can be erased if the media becomes too hot. And this is why companies like Google, for example, need to build sophisticated refrigerating systems with cold water, as you can see here. Some other companies, for example, Microsoft, likes to bring data centers under the ocean so that they are naturally refrigerated. And for example, Facebook installs some data servers in cold countries like Sweden. But what can we do in the laboratory to minimize the problem of heat dissipation? Now, basically, we can try to replace the use of current, as I've shown you before, with electromagnets to generate the magnetic field, with the use of voltage without current. So basically, the idea here for magnetoelectric actuation is to have like a capacitor where we apply some voltage without any current here, so that there is no heating, no Joule heating effect. And then the idea is that this voltage can be used to manipulate magnetism. The question, of course, is whether if it is possible to control magnetism with voltage. And actually, this brings us to the field of magnetoelectricity. This actually was predicted in 1894 by Pierre Curie, who predicted the intrinsic magnetoelectric effect. So in some materials where the magnetic and electric orders can be coupled to each other, so that, for example, you can control electric properties with magnetic fields and vice versa. The first experimental observation of magnetoelectric effect was done in 1961 in chromium oxide. And then from then, there have been a number of materials, including single phase, but also composites, where basically you can use voltage to control the magnetic properties. For example, it can be particulate composites, it can be laminated composite, it can be columnar, or what people nowadays, some people call these vertically oriented pillars or media. It can be nanoporous materials or even strain gradient mediated magnetoelectric effects. And here is a review from our group if you are interested. Now, what are the different ways to control magnetism with voltage? The first and maybe most used effect is the piezoelectric magnetostrictive effect in composites on bilayers, where basically you apply a voltage, then the piezoelectric deforms, and adjacent to this piezoelectric there is a magnetic layer which gets also deformed, and due to the inverse magnetostriction effect there are some changes in the magnetic properties. The problem of this mechanism is that if you grow this bilayer by layer on top of a rigid substrate, the amount of strain can be limited due to the clamping with the substrate, because this is adhered to a substrate which is rigid, and then if there is no strain, there is virtually no magnetoelectric effect. Then if you have self-standing structure, the problem can be another one, is that after actuating many times and deforming this many times, at some point there can be fatigue problems and the two layers can become detached. So people have been searching other different mechanisms to control magnetism with voltage, and another one, for example, is charge accumulation. This was reported in the late 90s and early 2000 in low temperature semiconductors and metallic ultra-thin films, where people reported that if you apply voltage in alloys, for example, iron platinum or iron palladium, you can tune the coercivity of these alloys simply because the accumulated electrostatic charge can cause changes in the electronic band structure of this alloy. But to observe this effect, in particular for metallic films, you need to prepare very, very thin metallic films, like maximum 2 nanometers. Why? Because electric field in metals is screened at the surface of the material. So this has limitations in terms of the type of layers where this can be observed. To overcome this, people, here, sorry, not yet. So here is what I was explaining in iron platinum, for example, that by applying voltage, you can have a change in coercivity. This was reported by the group of Dominic Givort in 2007. And you can see here what I was saying, that depending on whether there is electric field or not, the magnetocrystalline isotropy energy can change. And this provides an explanation why the coercivity of this ultra-thin iron platinum or iron palladium layer can be tuned thanks to the accumulation of electrostatic charges. But as I was saying, this is limited to ultra-thin metallic films, and to overcome this, people use another mechanism, which is Magneto-ionics, and this is what I'm mainly focusing in this presentation. What is Magneto-ionics? It's the change of magnetic properties due to the voltage-driven ion motion. So if you have, for example, the most simple case you could think of is, for example, a redox reaction where you have an iron film, you immerse in an aqueous electrolyte, you apply voltage, and then this iron gets reduced or oxidized, have a redox. Of course, this will change the magnetic properties of iron. But magnetoionics goes a bit beyond the simple redox reaction. For example, you can have a composite material, particulate or a thin film, coupled with an ionic conductor, and then you can use voltage to move, to induce the motion or the exchange of oxygen and ions between the ionic conductor and the metal, the same here. And this can be used, for example, to increase or decrease the overall magnetization of the composite or to change the coercivity. Another mechanism exploited in some of these papers is ion intercalation. So if people, for example, also use iron oxide, they immerse this in a lithium electrolyte, typical from batteries, and then the lithium can be incorporated in the iron oxide when you apply voltage. And this changes the magnetic properties of the iron oxide. So this magnetoionics causes non-volatile effects or permanent changes. It remains after you remove the sample from the electrolyte, but the drawback here is that it's usually very slow at room temperature. Why? Because ionic conductivity is a thermally activated process. Now you can use two types of electrolytes. You can use liquids, as I was explaining, but also solid electrolytes. Here are some papers. You can move different types of ion species, for example, oxygen, lithium, but also people now try to move protons, hydrogen, which is much faster than oxygen, or even nitrogen, as I will show you in the second half of my presentation. Interestingly, 3 years ago, it was reported that magnetoionics actually can be used to mimic the synapses of the brain, the way the synapses work. For example, in this paper, by applying voltage to cobalt gadolinium oxide bilayer, the authors showed that you can either increase the magnetization or the whole resistance or decrease it. So if you make an analogy with the brain, the increase of magnetization would be a learning process, and the decrease of magnetization would be like forgetting process. And this is multi-state. It is spike time dependent, and there were some functionalities reported in this paper, if you are interested, showing that actually magnetoionics can mimic the way the brain functions, which is not surprising, right? Because in the brain, there are these ion channels and everything is controlled by electric impulses. And here we are doing the same. We have a system that depends on ion motion and it's controlled by electric voltage. And actually, this is interesting because the brain is actually a very, very energy efficient memory that occupies a very tiny space of about 2 liters, and it consumes only 20 watts. The brain consists of 10 to the 15 synapses interconnected by neurons. Okay, now let's focus a little bit on what we do. And here I will explain first of all what kind of, so all what we do here, all what I will present is using a liquid electrolyte, which is propylene carbonate. And this is a non-aqueous electrolyte. We want to avoid the redox reaction. We just want to induce exchange of nitrogen ions or oxygen ions between the layer of interest and the liquid without any extra redox coming from the liquid itself. So all the oxygen or nitrogen comes from our sample. And this propylene carbonate contains traces of sodium, which allow to form the electric double layer. And this is very interesting because electric double layer is a very thin dielectric layer that forms at the interface between the material of interest and the liquid, and it is very narrow. It's only 1 nanometer, which means that we can induce ultra-high electric field with moderate voltages. Remember that electric field in a capacitor is voltage divided by thickness. So here with such a small thickness, we can generate very large electric fields with moderate voltages. Another advantage of this electric double layer formation is that if instead of a thin, dense film, you immerse there, for example, a nanoporous alloy, this liquid can penetrate inside and there are no pinholes, right? So you can actuate the whole structure like a sponge. We have some papers on this, which I'm not going to talk, but if you're interested, I'm sure you can find them. So now let's move to cobalt oxide. First of all, cobalt oxide at room temperature is paramagnetic, at low temperature is antiferromagnetic. And what we want to show here is that we start with a paramagnetic spinel structure. We want to apply voltage to induce the motion of ions, oxygen ions, to the liquid. For example, that was the initial hypothesis, right? To remove oxygen, to create vacancies, and then locally there will be some cobalt-cobalt exchange interaction. So locally, maybe we can generate ferromagnetic response. That was the original idea. Let's see if this worked properly. But first of all, here is a characterization of the as-grown cobalt oxide dense films. Actually, they were about 100 nanometers thick. So you can see here that we are not limited to 2 nanometers as in the works of charge accumulation that I've shown before on iron platinum or iron palladium. Here the layers are relatively thick and there is a columnar growth. They are polycrystalline. You don't need epitaxy. Actually, grain boundaries here are good. And you can see here that they have some texture and that the M versus H dependence at room temperature is paramagnetic. We don't have any magnetic signal as expected. And now here is what happens when we apply minus 10 volt for 1 hour. We start from a paramagnetic response, the black curve here. We apply minus 10 volt for 1 hour and you can see that suddenly, well, not suddenly, in 1 hour actually, you generate a ferromagnetic response. Then interestingly, if you apply, for example, 20 volt for 2 hours, we remove all this ferromagnetic response. So effectively, we're able to switch on and then switch off the ferromagnetic signal of this layer in the same way as you would switch on and off the light of a lamp, for example, or a computer. So we call this magnetic switch, voltage-driven magnetic switch. Now you can see here this is low, that you need relatively high voltage and so on. So the next slides is to further understand what happens and to try to make things faster. So just here to show that the things can be modulated with time, keeping the voltage constant. For example, here the longer the time, the larger is the magnetization. And for example, here you can see progressive increase of magnetization with time. Or you can keep the time, for example, to 1 hour and just increase the voltage you apply. You can see that also the magnetization scales with the voltage. And actually, for example, to have an idea, at minus 50 volt for 1 hour, the moment we generate is equivalent to 6 nanometers thick cobalt film. So we started from 100 nanometers thick. It means that we have a 6% conversion from cobalt oxide to cobalt, to metallic cobalt. We perform XPS analysis to try to understand what happens. And as you can see, first of all, the as-prepared sample contains this is the pattern, the experimental pattern, which can be fitted just from peaks corresponding to cobalt 304. With a little contribution from cobalt monoxide. After we apply minus 10 volt for 1 hour, you can see a broadening of this peak that can be fitted with adding an additional contribution here in green, and here for the energy position corresponds to metallic cobalt. So this is an indication that we are indeed forming metallic cobalt. If we increase the voltage to minus 200 volt, this peak from metallic cobalt becomes very obvious, as you can see here. Now, if we stop at minus 10 volt and then we apply plus 20 volt, you can see then that we recover the original pattern. So basically, this seems to indicate that we are generating metallic cobalt and then oxidizing it again, depending on the polarity of the applied voltage. To confirm this hypothesis, we perform high-resolution TM. In the as-prepared material, you can see here that there are spots from cobalt 304 and cobalt monoxide. And when we treat the sample at minus 200 volt for 30 minutes, additional spots appear in red here, and they correspond to metallic cobalt. And if you do the inverse fast Fourier transform, you can even find the location of these cobalt nanocrystals. Then, if we perform energy filter TM, you can see that after treating the sample, there are regions in the layer that become rich in oxygen, and other regions become rich in cobalt. Okay. This is better seen by yields. The first row here is the as-prepared state. You can see that the contrast is homogeneous and it corresponds to about 40% cobalt, 60% oxygen. So this is cobalt 304 more or less. But when we apply voltage, there are channels basically, so regions where the cobalt is actually the amount of cobalt is depleted, and we have enrichment in oxygen. And this seems to correlate a little maybe with the columnar growth of the film. Because it was columnar, maybe the oxygen migration takes place preferentially along grain boundaries. Now, to further understand and complicate things a little bit, we send the samples to our colleagues in Rossendorf, where they do positron annihilation lifetime spectroscopy. I don't have time, and even I would say I don't have the expertise to explain, to give all the details about this technique. But basically, this technique is used to characterize vacancies. And depending on, so what you do is to radiate the sample with positrons, and then you measure the time it takes for the vacancies to be annihilated, so you are sensitive to vacancies and other defects. If the lifetime is very small, it corresponds to vacancies inside the grains. If the lifetime is a bit larger, to the grain boundaries, and it's very large, which means here up to 4 nanoseconds, means like really voids, like porosity. But we don't have this. All the times we have in our experiments correspond to vacancies inside the grains or the grain boundaries. Then you can do, well, actually, our colleagues did some calculation using this atomic superposition method. And the conclusion is that from the times we get, actually, we don't have only oxygen vacancies. So we have like complex vacancies which involve cobalt and oxygen at the same time. So the initial picture I showed where you remove one oxygen ion and leave a hole is not true. Here we have formation of complex vacancies involving several atoms of cobalt and oxygen. That's mainly the conclusion from this technique. Then what we also did is to compare what happens if you use the capacitor configuration that I was explaining at the beginning, where basically you grow cobalt oxide on top of a conducting layer. This case is titanium nitride, it's conductive like copper. And then you have a large effect, as I've shown you now in the previous slides, or the transistor-like configuration where you grow the layer on top of silica, and then you kind of induce the effect laterally, and it's smaller, but it is there. This we did because some people for Magneto-ionics use the transistor-like configuration, some others capacitor-like, and well, the capacitor works better, as you can see here. So basically, these curves are consecutive hysteresis loop. The as prepared is black. Then we apply minus 50 volt, if I remember well, here was minus 50, yes. Then the first loop is the blue one. So we start at saturation, there is no signal. And then as you are measuring the hysteresis loop, the magnetization is increasing. And this is why this first blue loop has this strange shape, and it's not closed. But after several loops, for example, between minutes 225 to 250, you can see that the loops are closed and we saturate the effect. And the same here, but you can see here that you need a lot of, the effects are much lower, basically. Actually, you can see here the two configuration, the capacitor configuration, the transistor-like configuration. You can see that for the capacitor, MS increases fast and then saturates. For the transistor, it takes time and the amount of generated cobalt is much smaller. This can be understood from using COMSOL simulations because in the case of capacitor configuration, the whole layer is affected by the electric field because it is grown on top of this titanium nitride, which is conductive. But in the transistor-like configuration, the electric field is just accumulated at the place we make the contact. So basically here, where we apply the voltage. And therefore, it is limited a little bit. The lateral movement of oxygen is limited and the effects are much smaller. In both cases, nevertheless, we have good cyclability. We can induce these on-off transitions many times. Here, this black curve is shifted for clarity, but it should be at 0. This is artificially moved upwards to compare the two, but it is between 0 and something, 0 and something. We are generating this magnetic signal and removing it. And for the capacitor, minus 4 volt is enough. For the transistor, we need minus 10 volt. Okay, then the effects are, as you have seen, they are relatively slow. It takes like minutes or even hours to generate the things. And we want to improve this. So what we did is to think of another system that maybe works faster. And we thought about cobalt nitride. Cobalt nitride is cubic. It can be grown by sputtering, the same as cobalt oxide. And what is important is this, what I'm explaining here, is that the electronegativity between nitrogen and cobalt is lower than between cobalt and cobalt oxide and oxygen, sorry. So cobalt nitride bonds are weaker than cobalt oxide. So maybe it is easier to remove nitrogen from cobalt nitride. And cobalt nitride, by the way, is also non-magnetic at room temperature, so very analogous to cobalt oxide. Now, what happens if we compare cobalt oxide and cobalt nitride for a given condition, the same thickness of the layers and so on, we apply the same voltage? You can see here that cobalt oxide is what I've shown before, this loop that increases with time while we are measuring. And here is the same for cobalt nitride, but the difference is that for cobalt nitride, after measuring the first loop, 25 minutes, we already reach a saturation magnetization that doesn't change upon consecutive loops. So that between 50 and 75 would be the third hysteresis loop. You can see the magnetization did not change. So everything happens for cobalt nitride in 25 minutes, whereas for cobalt oxide, it takes even more than 50 minutes to still see a change. Actually, if you see here the dependence of MS with time, you can see that for cobalt nitride, it is indeed very fast and it saturates. And for cobalt oxide, it takes a lot of time, several hours, to reach this steady state. Another thing is that the onset voltage for cobalt nitride is a bit lower, and in the two cases we could have good cyclability of 10 to the 100 cycles. Now we did the same experiment, the same structural characterization like before for this cobalt nitride. So you see it's off in the as prepared, -4 volt, and it's on ferromagnetic, +4 volt is again paramagnetic. Here is the yields from before, from the previous slides, and here is the yields for cobalt nitride, and it's a bit different. For cobalt oxide, there is this enrichment in cobalt or oxygen in a little bit in random regions, but for cobalt nitride, the nitrogen seems to be removed layer by layer, and when you apply voltage, you form this kind of bilayer. So the as prepared sample is homogeneous. You can see here the platinum from the top contact to prepare the lamella, the cobalt nitride and the copper. We apply -50 volt, we have the copper, we have the platinum, but here inside cobalt nitride there are two layers, and one of them is more rich in cobalt and less, and it contains, the upper one contains less nitrogen. So this might be interesting for devices because you apply voltage, you have a bilayer. For the two systems, cobalt oxide and cobalt nitride, we have good cyclability. Actually, for cobalt nitride, it's enough to apply -4 volts, so we are decreasing the voltage. And it works very well. And then what we want now is to further increase the time. No? All I've shown here, even if it's nitrogen works faster than oxygen, I've shown that you need something like half an hour, like 25 minutes to reach this steady state equilibrium. But we want to speed up the process. So what we did is to reduce the thickness of the layer of this cobalt nitride. And you can see here that when you reduce the thickness of the layer from 200 nanometers to 5, especially if you make a zoom at the beginning, you can see that for 5 nanometer, already in 1 second, we generate magnetization. So we can induce this off-on transition to reduce the time from 25 minutes to less than 1 second just by decreasing the thickness of the layer. And then another thing that we did is now to think about neuromorphic computing. We have to apply pulses. So the brain works with voltage impulses. It doesn't work with a DC voltage, right? And what we did here, we took cobalt nitride, which is the fastest system, and we compared what happens when we apply a DC voltage or when we apply voltage pulses, for example, between 0 volt and -25 volt at different frequencies. We did this for 200 nanometers thick layer and 25 nanometers thick layer. Let's focus first on the 200 nanometers. What you can see here is that if you go very slow, like 1 hertz, the magnetization almost does not increase. And if you go very fast, 100 hertz, it increases much faster. This is analogous to what happens with the brain. Because imagine during this almost 1000 seconds, at 100 hertz, you will have a lot of stimulus, right? It's the same as when we see an image or something, and we see it many, many times, it is retained better in the brain, right? So this behavior, this frequency behavior, is analogous to what happens in the brain, and it's called spike time dependence memory. and it shows a transition from short-term memory to long-term memory after repeated impulses. Now we want to understand why if you go slowly doesn't work very well, right? And this I will show you showing the results for the 25 nanometer, where again you can see here that the faster you go, the larger is the magnetization. And what is interesting, by the way, here is that this 100 hertz. This 100 hertz means stimulus of 10 milliseconds. So this experiment also shows, besides all these neuromorphic things that I will explain in detail later, that in voltage pulses of 10 milliseconds, it is possible to induce magnetization. So chronologically, we went from something that you need 1 hour to induce the effect to something that works already in milliseconds. And this, we think, is a very good improvement. A millisecond is actually the frequency, the time scale in the brain. The brain doesn't work faster. In computers, we need nanoseconds, but in the brain, milliseconds is enough. Now let's focus on the 25 nanometers layer, which is, it shows some interesting effects. The first one I want to show is that if we go very slowly, the signal is lower. And we want to understand this. And actually we measured slowly here, this zoom B is this area, this region here. And there is a correlation between when we apply the voltage and we stop. And you can see that what happens here is that when the voltage is applied, so minus 25 volt, we have an increase of magnetization, but when we stop the voltage, there is time for relaxation. So each time you stop, there is relaxation of the effect. So at the end, if you go very, very slowly, what happens is that you don't induce so much effect, simply because during the voltage application, the system is relaxing all the time. But there is here even another interesting observation, and this is this comparison between the blue and the red curve. The blue here is a 25 nanometers DC, the voltage is applied DC for 600 seconds. And what you can see here is that when we stop the voltage, there is no relaxation, but the magnetization continues to increase. And this is a very fancy effect that cannot be mimicked with other types of neuromorphic materials like resistive switching or spintronic materials. It's hard to obtain this behavior. I will explain why this happens, or hypothesis we'll have later. But this would be analogous to what happens in the brain when we sleep. In the brain, when we sleep, the memory is retained further. And this is a bit what happens here. We stop the stimulus, we stop, and the magnetization continues to increase. But before explaining this, why this happens, it is important to show that there is a correlation in this cobalt nitride between electric properties and magnetic properties. Why? Because the change in magnetization is not how the brain works. The synapses are interconnected by electric stimulus. So it is very important to have a correlation between electric resistivity and change in magnetization. And actually there is such correlation, and we have this paper published this last year. If you change the nitrogen partial pressure of the layers, when we grow the layers by sputtering, you can see that you can modulate the resistivity. And depending on the type of sample and what resistivity value we have, there is a different magneto-ionic response. This is something we need to further investigate in situ. We want to measure in situ the resistivity of the layers, how it changes when we apply voltage. But for the time being, this correlation between electromagnetic properties exists here, which is good for neuromorphic, especially for synaptic functionalities. Now let's go back to this fancy effect, which is still now the paper is under review, still not published. What happens here? Why, if we stop the voltage, why in DC, why it continues to increase, but this does not happen at 0.01 hertz? And what we think here, and this is just a hypothesis, is that if the layer is very thin, like in this case, you have seen that magneto-ionics is very fast. So the effect is induced in less than 1 second. But in order to release this nitrogen to the liquid, to the propylene carbonate, there is one of the steps that needs to happen is that the propylene carbonate chains are able to solvate, to absorb the ions. Only if this is possible, the nitrogen can go away from the film and the magnetization increases. We think that if you go too fast, and for thin layers, what happens is that there is a nitrogen accumulated here, and somehow the propylene carbonate chains become saturated with nitrogen. The nitrogen cannot go out simply because there are no more free chains. When we stop the voltage, the electric double layer is destroyed, and then new chains arrive from the liquid and take the nitrogen that was accumulated at the interface and then the nitrogen further goes to the liquid, and this would allow for the magnetization to be further increased. This is a hypothesis, but we already did some elastic recall detection analysis, which is a technique that gives you a little bit an idea of the nitrogen profile across the depth of the film. And if the profile is symmetric, means that the nitrogen content is more or less homogeneous. If it's asymmetric, means that the nitrogen content is not homogeneous, that nitrogen is accumulated at some height. And here you can see that the as-prepared film nitrogen is symmetric, but the profile becomes asymmetric when we apply voltage. So this seems to indicate that there is indeed this nitrogen accumulated at the interface. Now, in conclusion, what I've shown here is that in some particular systems like cobalt oxide, cobalt nitride, when you apply voltage, you can induce the most drastic change that you can imagine in magnetism, which is to completely suppress magnetic properties or induce them again. This goes beyond the typical observation of people that see a reorientation of the easy axis of the loop, or changing coercivity, or changing magnetization with voltage. So here we completely suppress or generate magnetic properties. I've shown you that this can be done both with nitrogen transport or oxygen transport, that the nitrogen transport is via plane wave-like migration, which creates like bilayers, which is interesting. And also nitrogen is faster and with lower onset voltages than oxygen ion migration. And in particular, if you do dynamic effects, there are some functionalities that can mimic some of the properties of the brain. So I would like to finish my presentation thanking all my collaborators from my group, PhDs and postdoc people, and also collaborators from different universities like the Kathleen of Nanotechnology, Spintech in Grenoble, Georgetown University, the group of Kai Liu, and our collaborators that perform this positron ion annihilation spectroscopy experiments and so on. Here is the thanks to the supporting agencies, the funding agencies, and I would like to thank you very much for your attention. Good. Maybe I should stop sharing or not?
No, it's okay. Thank you for your very nice presentation. Really amazing all the work that you have done. I would like to open the session to questions. I don't know if you want to switch to English or to Spanish.
Como queráis, me da igual. As you prefer.
Ok, bueno, pues podemos pasar a la ronda de preguntas si quieren. Yo tengo algunas preguntas. De nuevo, muchas gracias, Jordi, por la presentación. No sé si alguien quiere comenzar, si no, comienzo yo con las preguntas. Bueno, empiezo yo mientras se van animando. En la diapositiva 15 habías mencionado que en el sistema no tiene pinholes. Cuando te refieres a pinholes, eso quiere decir similar a lo de una barrera aislante, ¿no? Una juntura o algo así. Que tienes una capa homogénea de...
¿Ves la slide en cuestión o no?
Ahora no estoy viendo, estoy viendo tu pantalla, tu escritorio.
¿Y ahora? Es que tengo dos pantallas, esto complica un poquito. ¿Ves
ahora sí. Sí, ahora sí se ve.
Es la slide, vale. Sí. Es que de esta forma me puedo mover por las distintas slides. Cuando se intenta hacer el mismo experimento en solid state, lo que ocurre es que muchas veces cuando aplicas voltaje, el dieléctrico no es suficientemente bueno y por los defectos estructurales del dieléctrico, por ejemplo MgO o alúmina o hafnia, hemos probado varios, fácilmente empiezan a conducir electricidad, con lo cual no se acumula carga eléctrica y hay Joule heating effect. De hecho, la muestra se quema, literalmente, a veces, ¿no? Entonces, esto no ocurre cuando utilizas un liquid electrolyte dieléctrico. No ocurre porque se forma con los iones, se forma esta electric double layer, que es algo complicado. Hay distintos modelos de formación de electric double layer, pero esto no ocurre, puedes mantener altos voltajes durante el tiempo y no pasa nada. Bueno, el propilencarbonato se acaba degradando, pero no hay pinholes, en el sentido de que no hay shorts, electric shorts, no hay cortocircuitos. Esto es lo que me preguntabas, ¿no?
Sí, está bien. Después, en las medidas de BCM, me da... no sé, o sea, ¿cómo manejas la vibración del líquido? O sea, estás vibrando el líquido también, ¿no?
Sí, 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 esto de hecho es muy sencillo, bueno, sencillo, es un poco rudimentario lo que tenemos, pero lo más sencillo posible, te puedes imaginar, es un Eppendorf, de hecho esto que hay aquí dibujado tan bonito,
Ujú,
es muy bonito, pero en la práctica es un Eppendorf con un tapón donde básicamente hay el Eppendorf, nuestro BSM, es de Microsense, tiene la ventaja, y también los de Lecture, que es abierto.
sí.
Entonces tú ves la caña, tú ves la muestra, no está como un squid que está dentro y no tienes acceso a la muestra, aquí la ves, ¿no? Entonces lo que hacemos es pegar el Eppendorf, que dentro hay la muestra con los contactos eléctricos y hay un counterelectrode de platino, que aquí se indica, y este pelo está fijado al holder y vibra y no pasa nada, y mide igual. Es decir, mide igual que mide sin líquido. ¿De acuerdo?
Pero la muestra
Sí,
debe estar pegada al Eppendorf también, ¿no? O sea, debe estar sujeta al
está fija, sí, sí. No está pegada literalmente, pero de alguna forma está fijada allí, sí, sí. Está,
Está bien.
queda,
Después,
digamos, encajada con el espesor del Eppendorf, queda encajada y se mueve con el Eppendorf, se mueve todo.
bien.
Únicamente aparecen problemas cuando hay bubbling, cuando hay burbujeo, burbujas. Esto ocurre a veces cuando aplicamos mucho voltaje. Este nitrógeno se va al líquido, como he explicado, pero el nitrógeno tiene, o sea, el líquido tiene un límite de solubilidad no muy elevado para el nitrógeno. Entonces hay un momento que se aplica mucho voltaje, este nitrógeno 3 menos, que son los iones de nitrógeno de la capa, se van al platino, el counterelectrode, y allí se forma nitrógeno cero gas. Entonces a veces sí que cuando hay muchas burbujas, estas burbujas acaban produciendo que el Eppendorf, digamos, no se abre, pero hay como porosidad, sale aire fuera y líquido a veces. Es decir, sí que tenemos a nivel, ya que me preguntas sobre la parte más de detalle de experimento, sí que es verdad que si vas a voltajes muy elevados, puede haber el problema de burbujas y a veces esto hace que ceda el Eppendorf un poquito y sale líquido. Entonces ahí sí que hay que tener cuidado.
Una pregunta, Jordi.
Sí,
Bueno, ante todo, felicitaciones por la charla. Me
gracias.
quedó una duda, en el caso de óxido de cobalto, si la película es demasiado delgada y se forman esas estructuras columnares cuando se reduce el oxígeno, el óxido, ¿no hay chances de que se forme un cortocircuito por el cobalto metálico que se forma?
No lo hemos visto, no lo hemos visto y no se podría producir en el sentido de que, es decir, este líquido es aislante, es un dieléctrico. El platino está en el otro lado. Entonces, aunque aquí empiece a conducir, no puede haber un short porque simplemente con el líquido no llega, no puede ocurrir. Lo que pasa es que la forma como se acumulan las cargas sí que cambia. Eventualmente, si todo es conductor, igual sí que llega un momento en que el fenómeno se para, ¿no? En el sentido de que la parte que es metálica, el campo eléctrico ya no está tanto en la interfase, sino entre el cobalto y el cobalto oxide. Se complica un poco la cosa, ¿no? Pero shorts no, en el sentido de que no se puede llegar al counterelectrode porque está lejos, digamos, está como medio centímetro, unos milímetros de separación de la muestra.
Ok, gracias.
Elin tenía una pregunta, me parece.
No te escucho, Elin. Habla muy... A ver, prueba a
Creo que
hablar.
estás con el micrófono arriba, me parece. Estás con el micrófono en la cabeza.
Acá.
Ahora.
Sí, gracias Luis, estás en todo. Bueno, súper interesante la charla, Jordi, la verdad, muy
Muchas
bien los
gracias.
resultados. Lo que te quería preguntar es acerca de la difusión del oxígeno, si vieron una dependencia con la morfología de la muestra, es decir, si se da más por bordes de grano o más adentro, tipo, bueno, macizo dentro de la película delgada, y cuál es la diferencia con el compuesto de cobalto, con los nitruros, digamos, que es más superficial. Si podés comentar sobre eso.
Sí, sí, es algo que no tengo una respuesta definitiva, es algo que estamos investigando. Por un lado, queremos preparar por PLD cobalto oxide epitaxial con diferentes orientaciones y sin grain boundaries. Y ver si se ven lo mismo, si hay magneto-iónica o no, y si hay alguna orientación privilegiada o no. ¿Vale? Esto es algo que queremos hacer, pero sí hemos visto, bueno, no lo sabemos o sea, no lo podemos asegurar, pero sí que muchas veces se ve estos perfiles como era crecimiento columnar de cobalt oxide, como si pareciera que por allí, por las grain boundaries, es por donde difunden mejor el oxígeno. Hay muchos trabajos de memristors y demás, de varios óxidos, que reportan algo similar. En la grain boundary la movilidad iónica es más grande que dentro. ¿Qué pasa con el cobalt nitride? El cobalt nitride es más amorfo, muy nanocristalino. Entonces podría ser que esto influyera en el por qué, en este caso, se ve como si el nitrógeno saliera como layer by layer, como una cebolla. Se va una capa, se va otra capa. Y no sigue estos perfiles tan, digamos, transversales a través de la capa. Pero tampoco lo sabemos seguro. Igual tiene que ver más con la resistividad, ¿no? Porque aquí hay un tema complejo. Si el cobalt nitride es muy metálico, el campo eléctrico es solo en la superficie. Pero luego si lo reduce, o sea, si el nitrógeno se mueve, puede ser que cambie la propiedad eléctrica. Es algo que tenemos que estudiar in situ, no lo hemos hecho. Puede ser que el cambio de propiedades eléctricas haga que el campo eléctrico penetre más o menos y empiece a influir, digamos, solo en la upper layer o más adentro y demás. Y esto también permite la formación de esta bicapa, ¿no? Es algo complicado, pero la microestructura entre cobalt oxide y cobalt nitride es un poco distinta. El cobalt nitride es más amorfo, muy nanocristalino, igual esto afecta.
Otra pregunta por aquí. Muchas gracias, Jordi. Encantado, la charla fue muy linda. ¿Puedes hacer las analogías? Porque has hablado de los main resistors, hemos escuchado eso, no es que hagamos nosotros, pero ¿cuáles son las analogías y las diferencias con esto de usar electrolyte y lo que podría venir de los main resistors como devices, digamos?
Sí, parece, al memristor hay canales electrónicos de conducción y canales iónicos, depende de los trabajos y del sistema, hay distintos mecanismos. La analogía más obvia aquí sería cuando el memristor funciona también por migración de iones, que hay trabajos que son así. De hecho, hay algún artículo de nickel oxide, recuerdo, donde estudiaban las propiedades memristor y magnéticas al mismo tiempo. Níquel oxide es antiferro, entonces a medida que el oxígeno difundía se formaba níquel y veían cambios de propiedades eléctricas y magnéticas. Se parece bastante. La analogía en este caso funcionaría bastante bien. Los timescales also también son de milisegundos, es decir que...
Okay.
¿Y el electrolyte que usas, que dices que es no conductor, pero ¿qué es?
Es propilencarbonato, es el electrolyte. De hecho, aquí no nos complicamos mucho la vida en el sentido de que tomamos el electrolyte, a ver dónde está, el electrolyte de este artículo del Science de Sort, donde usaban el propilencarbonato, pero no es propilencarbonato solamente, propilencarbonato es un dieléctrico líquido, pero para que funcione bien se tiene que formar la double layer, tiene que haber iones allí. Entonces, por un lado, lo que hicieron en este grupo y lo copiamos o lo adaptamos, es tener dentro del propilencarbonato durante un tiempo sodio metálico, y este sodio reacciona, si hay por ejemplo trazas de agua del ambiente, humedad, reacciona con el agua y se forma sodio más y se forma OH menos, es decir, formas cationes y aniones. Y esto es lo que permite, de hecho se ve aquí, estos iones van, cuando aplicas voltaje negativo, los sodios se va aquí, y en el otro lado se va el OH y te permite formar la double layer.
Claro.
Tengo que decir que esto es lo que nosotros hacemos, pero hay otra gente haciendo magneto-iónica y utilizan ionic liquids, y otros utilizan incluso agua con KOH. Hay varios tipos de electrolitos que podrían funcionar. Nosotros usamos pero hay otras posibilidades. En este hay un review por ahí, no sé si lo he citado. Creo que es el APL Materials del 2019, que es nuestro. En este artículo hay tablas de varios sistemas, de varios electrolytes, de varios efectos, de porcentajes de cambio de todas las propiedades, etc. Y allí podéis ver todas las posibilidades en cuanto a líquidos que se pueden usar.
Bueno, muchas gracias.
De nada.
Jordi, yo tengo otra pregunta. En la diapositiva 30 habías mostrado las curvas de magnetización, de la saturación, perdón, cuando llegan a un estado estacionario.
Sí.
Ahí en la gráfica de la derecha, antes de llegar al estado estacionario, sube un poco la magnetización y después vuelve a decaer, ¿no? Ahí,
Esto podría ser en el cobalt nitride, aquí,
sí,
¿no?
sí.
Podría ser. Sí. No, bueno, de hecho no podría, de hecho es. Sí, sube y luego baja un poquito. Es algo que no hemos estudiado, no te puedo decir por qué sucede esto.
Está bien.
A ver, sí que es verdad que el nitrógeno, bueno, pues por ejemplo, dependiendo de cuánto nitrógeno hay, pues puede saturar el líquido, luego puede haber fenómenos de relajación y demás, pero aquí estamos aplicando de forma continua este voltaje, entonces la relajación no explicaría esto. La verdad es algo que no lo sé, de hecho no lo sé. Tendría que ser que se forma cobalto y de algún modo este cobalto pues se vuelve a nitrurar de alguna forma. Podría tener que ver con la formación de esta bilayer y cómo evolucionan las cosas con el tiempo, pero es algo que de entrada no te sé explicar por qué. Es así, sí, es una buena observación.
Ok, ok. Bueno, de nuevo, si no hay más preguntas, te agradezco, Jordi, por la charla muy linda que nos acabas de dar. Y con esto, nada, eres bienvenido
Bueno,
a dar tu charla, una charla en nuestro grupo cuando quieras.
pues muchas gracias por la invitación y espero que os haya gustado y que lo habéis encontrado interesante. Y si algún día tenéis ideas para colaborar o queréis algunas medidas o al revés, pues estamos en contacto.
Totalmente, ese es el
Vosotros
objetivo de estas charlas.
y cualquiera que esté en la audiencia, pues lo mismo. Muchas gracias a vosotros.
Ok, gracias, Jordi.
Que tengáis una buena tarde.
Muchas
Igualmente,
gracias.
hasta luego.
Muchas gracias, Jordi.
Perfecto.